So here is a common problem in mathematics. I am given an implicit relationship involving two variables x and y, and I want to find the derivative dy dx. For most of this lecture, I will call this derivative y prime. For example, my implicit relationship may be given by x squared plus y squared equal to 1, and I'm looking for the derivative of y with respect to x. Now, if I have an explicit relationship where y is determined as a function of x, we simply go ahead and differentiate the function with respect to x using standard rules. For example, if y is equal to x squared, we have y prime equal to 2x. It's clear that the derivative y prime is defined even when we have an implicit relationship between x and y. Remember, y prime is the change in y when we make a small change in x. If we have an implicit relationship between x and y, then if we make a change in x, this will typically require a change in y if the equation is to be satisfied. For example, if 4x plus 2y is equal to 6, and we consider x equal to 1 and y equal to 1, which satisfy the equation. Then, if we increase x to 2, then we must decrease y to minus 1 if the equation is to be satisfied. The derivative in this case, y prime is equal to minus 2. Y decreases by 2 units when x increases by 1 unit. We can also view the derivative as the slope of the tangent of the implicit plot. For example, the implicit plot of x squared plus y squared equal to 1 is a circle with radius 1. X equal to 0 and y equal to 1 satisfy the equation, and the tangent at this point is a horizontal line. And the derivative at this point is y prime is equal to 0. So here is the main question of this lecture. How do we find the derivative when the relationship is implicit? Well, we actually have a couple of ways of doing that. Perhaps the most obvious one is to turn the implicit relationship into an explicit one. For example, 4x plus 2y equal to 6 is equivalent to y is equal to 3 minus 2x, from which we immediately see that y prime is minus 2. However, in many cases, turning an implicit relationship into an explicit one forces us to solve an equation analytically, which can be difficult and in many cases impossible. Therefore, in this lecture, we will discuss an alternative method called the method of implicit differentiation. The basic idea behind implicit differentiation is to begin with the equation defining the relationship between the variables. We differentiate this equation with respect to x, and that will give us a new equation. This equation will contain y prime, and solving the equation for y prime will give us the derivative. In the latter case, the equation may be solved numerically. There is, however, a catch to differentiating the equation. When we differentiate the equation, we must treat the x variable and the y variable differently. Whenever you see an x variable, you differentiate it the same way you would if you were to differentiate the function of x. For example, if the left-hand side of the equation is x squared, the derivative will be 2x. Differentiating log x will give you 1 over x, and so on, same as before. However, the y variable must be treated differently. When we are looking for the derivative of y with respect to x, we must treat y as a function of x. For example, let's say that the left-hand side of our equation is y squared. We're supposed to differentiate the equation with respect to x, and we must view y as a function of x. Therefore, y squared must be viewed as a composite function. The inner function is y as a function of x. This function is unknown to us. The outer function is y squared. Remember the chain law? We are supposed to differentiate the inner function as well as the outer function. Now that may seem to create a problem as I don't know the inner function. However, this is not the problem. The derivative of the inner function is simply y prime, which is yet unknown. The derivative of the outer function y squared is simpler. It is 2 times y. By the chain law, the derivative of y squared is the product of the inner and the outer derivatives, that is 2y times y prime. Here is a complete example demonstrating the method of implicit differentiation. Our implicit relationship is 4x plus 2y is equal to 6. Let's differentiate both sides with respect to x. The derivative of 4x is 4. The derivative of 2y is not 2. We are differentiating with respect to x, not with respect to y. Y is a function of x and 2y is a composite function. The outer derivative is 2 and the inner derivative is y prime. By the chain rule, the derivative of 2y is 2y prime. Differentiating the right-hand side with respect to x gives us 0. Thus, we have 4 plus 2y prime equal to 0. The final step is to solve for y prime. 2y prime is equal to minus 4 or y prime is equal to minus 2. Precisely what we got by first converting the implicit relationship to an explicit one and then doing the ordinary derivative. Here is a slightly more complex example. The implicit relationship is x squared plus y squared equal to 1. Differentiate both sides with respect to x. The derivative of x squared is 2x. Y squared is a composite function with outer derivative 2y and inner derivative y prime. Thus, we have 2x plus 2y times y prime equal to 0. Moving 2x over on the other side and cancelling the 2's, y times y prime is equal to minus x. As long as y is not 0, we can divide both sides by y and we have y prime equal to minus x divided by y. From this, we can find the slope of the tangent at any point on the circle, except for the points where y is equal to 0. For example, at the point x equal to 0, y equal to 1, the derivative is minus 0 divided by 1, which is 0. The point x equal to 1 divided by square root of 2 and y is equal to 1 divided by square root of 2 satisfies the equation and is a point on the circle. X squared is 1/2 and y squared is 1/2 and the sum is 1. The derivative at this point is y prime equal to minus x divided by y, which is minus 1, which makes sense simply from a symmetry consideration. Here is another example which illustrates another important point in implicit differentiation. The implicit relationship is now 4xy equal to 1. As long as x is not 0, the implicit relationship can be turned into an explicit one. We simply divide both sides by 4x and we have y is equal to 1 divided by 4x. From this, we can easily find the derivative. Y prime is equal to minus 1 divided by 4x squared. Let's check that we get the same answer using the method of implicit differentiation. First, the left-hand side is a product of 4x and y, but remember, we must treat y as a function of x. That is, the left-hand side is 4x multiplied by another function of x. This means that we must begin by using the product rule. The first term in this product is 4x and the second term is y. By the product rule, we begin with the derivative of the first term, that will give us 4, and we multiply it by the second term, which is y. Then we do plus the first term, 4x, multiplied by the derivative of the second term. The derivative of y is the inner derivative only, that is y prime. The derivative of the right hand side is 0. The last step is to solve for y prime, and we have y prime equal to minus y divided by x. At first, this result seems to contradict the result we got from turning the implicit relationship into an explicit one, but it does not. Since y is equal to 1 divided by 4x, we can also write y prime is equal to minus 1 divided by 4x divided by x, which is equal to minus 1 divided by 4x squared. Whenever we find the derivative by turning the implicit relationship into an explicit one, the derivative will always be a function of x only. However, when we do implicit differentiation, the typical outcome is that the derivative will depend on x as well as on y. Only if the implicit relationship can be written as an explicit one can you turn the derivative into a function that depends on x only. We can use the same method to find the second derivative, y double prime. We simply differentiate the equation once again. Let's continue with the example 4xy equal to 1. Differentiating with respect to x gave us 4y plus 4xy prime equal to 0. Differentiating again, and we get 4 from the outer derivative multiplied by y prime from the inner derivative. Then a plus. For the next term, we have to use the product rule again. The first term we take as 4x and the second term we take as y prime. The derivative of 4x is 4 multiplied by the second term plus the first term 4x multiplied by the derivative of y prime. The derivative of the derivative is the second derivative, and we have y double prime. This equal to 0. Differentiating our equation a second time gives us 8y prime plus 4x y double prime equal to 0. Solving for y double prime, we have y double prime equal to minus 2y prime divided by x. Since y prime is equal to minus y divided by x, we also have y double prime is equal to y divided by x squared. You may, of course, reverse the roles of our variables x and y to find the derivative x prime or dx dy. In this case, you differentiate both sides with respect to y and treat x as a function of y. In the final step, you solve for x prime.